All right, guys. So new chapter here, chapter 23. And this chapter is on Faraday's law and induction. So we're going to look at some of the magnetic field applications. And Faraday's law is actually a very important contribution to understanding the applications of that, magnetic fields. And one of the things we have here is Faraday was trying to answer very, important question. So in let's say chapter 22, we learned that if you have a wire with the current running through that wire, that means basically moving charges, right? That means, or you can say electricity generates magnetic field. So we learned that there's this, magnetic field, like let's say all around this wire, right? And it's kind of like curls around the wire. And we can find, let's say, the strength and the direction of those magnetic fields using some of the Biot-Savart law or Ampere's law, right? But, the important thing here was that electricity was responsible for generating magnetic fields. So Faraday was trying to find the other way around. Is it possible then to generate, electricity from magnetic fields? So here we have electricity generating magnetic field. Now we want to know, can magnetic field generate electricity? Can we go other way around as well, right? And he did this by basically designing, half a dozen experiments where he would look at in terms of how he can generate, electricity from magnetism. Obviously, we're learning about it. That means he was successful in doing so. And through some of the experiments that, we're going to look at next, let's say 10, 15 slides, we can see the insight that he had by doing those experiments and the equation that he derived, right, and the law that he has, basically in understanding how you can generate electricity from magnetism. All right, so we're going to consider a loop of wire that is connected to some kind of ammeter, sensitive ammeter, sort of like a galvanometer. Okay. Now, this loop, right, so this is basically just some kind of conducting loop, right? So just some kind of conductor only connected to ammeter. Remember, ammeter itself is not a power source. It can only, record, presence of a current. So for example, right now, even if let's say you didn't have the magnet, imagine you didn't have this magnet at all. You connect this, let's say this loop to the ammeter, right? The reading will be 0, right? The reading will be 0 because it's not connected to any power source, no battery, no power supplies, and there will be no current in that loop. Okay. Now, one experiment he did was to have that current loop and then to have a magnet, a bar magnet. Remember, so right now we know of 2 sources that generate magnetic field. One source is the bar magnet, or sometimes is also known as a permanent magnet. Another source is the, a current in a wire. That's another source of magnetic fields. So let's look at in terms of this magnet. So what he did here is, let's say this is experiment 1. He held a stationary magnet, right? The magnet was stationary. And one thing we know about bar magnets, right, that they generate magnetic field. And you can see, right, those green lines are the magnetic field generated by the magnet. And you can see, right, all of those, magnetic field lines, at least, some of those, right, going through the, center of that loop. Okay. That means we do have magnetic field going through that loop, and that loop is basically in a region where there is a magnetic field perpendicular to its plane. Okay. Now, the ammeter, if you wait a few minutes, 5 minutes, 10 minutes, is not going to be recording any, current in the loop. That means while you have a magnet held stationary, there is no deflection of the ammeter. That means ammeter basically detects no current. Deflection or just reading, this is actually digital ammeter, right? So there will be no deflection, but a reading of the current, but it shows 0. That means there is absolutely no current. Remember, the way we define current is this. There are a lot of those, free moving charges, right, in that conductor. And they are right now moving, but they're all moving in a random direction. So there is no overall motion for those, charges in specific direction. Remember, when they all start moving in specific direction, right? Let's say, or being pushed in a specific direction, then that motion, like overall flow of charges, we can, call current. Now, if it records no current, that means, you see 0 over there, means those charges are not being, pushed or pulled in a specific direction. They're just basically moving randomly inside the conductor. All right, so no deflection of the ammeter. So there were no induced current. So what we're gonna call induced current would be then the current in this, loop of wire. Because remember, this loop of wire is not connected to any power source. That means if there is any type of current, it will be induced by those magnetic fields, right? So it will be induced by those magnetic fields, or the, external magnetic field. All right, so, and experiment 1 demonstrates that if you have, magnet that is held stationary next to this, current loop, it has no induced current. Okay, so again, it does have magnetic fields through the loop, but the, important thing about this configuration is that the magnetic field through the loop, right, through the center of the loop, doesn't change with time. That means if I come and measure this value over there, so the magnetic field at the center, right? So let's say I get 5 Tesla. Well, it's going to be 5 Tesla now, 5 seconds later, 10 seconds later, because, the position of the magnet relative to that center of the loop, right? This R, right? It doesn't change. That means the strength of the magnetic field, in this region will remain constant. All right, so you can say, right, even though the magnet is, inside the loop, that is, there is magnetic fields inside the loop, there is no induced current. Okay. So then what he did was moving magnetic field. So he started moving the magnetic field relative to that loop. So you can say, right, when the magnet moved toward the loop, ammeter deflects. Okay. And that deflection indicates a current induced in the wire. All right. Which means that instead of having the magnet, sitting there stationary, you move the magnet relative to the loop. And as soon as we move the magnet relative to the loop, there is an induced current. That means somehow all the charges in the loop start all moving in, one direction, which means, there is a current in the loop, and the ammeter detects that current. Okay. And you can see here is you're given the direction of the current, right, in the loop. So let's say in this case, it is moving in this direction. So let's say clockwise, right? So that means that you have more or less clockwise, direction current in that circular portion of the loop. If you have magnet moving, let's say, toward the wire. Okay. Now, he did now the opposite, which is moving the magnet away from the wire. Well, as soon as he did that, he again noticed there's a deflection in the ammeter. So the ammeter now again detects a current, but interestingly enough, it's a different sign. It was, negative before, now it's positive. And the current, which indicates that the current direction is changed. Now it is counterclockwise, okay? That means you get, again, induced current, right? Again, we get induced current, but induced current basically now is in opposite direction. So that's why ammeter deflects in the opposite direction. Okay, that means an electric current is set up in the coil as long as a relative motion occurs between the magnet and the coil. That means you could see, right? Experiment 1 was, holding that magnet stationary. So if you hold it stationary, there was no induced current. But as soon as you start moving, there was the induced current in that loop of wire. Why? Because think like this: if you're moving toward or away, if I'm looking at the magnetic field at the center, right, then what I'm going to get here is whatever value I get, let's say 5 Tesla, 1 second later is going to be different. Because, for example, in this case, see, magnet is moving away. That means magnet now a little bit later is going to be like this. So that means this distance will increase. Then it's going to be right here. So that distance from the, the magnet will increase, which means magnetic field will decrease in strength. In the previous example, when you had the loop, right, and the magnet was moving toward the loop. So let's say if I measure the magnetic field at the center, so this is my R1, then a little bit later, the magnet is here. That means my R here is smaller, and then the magnet is here. My R is even smaller. That means the magnetic field would increase inside the loop. That means you can see, right? When the magnet is moving relative to the coil, there is an induced current. Why? Because there is a change in magnetic field strength through the center of the coil when we do that. All right. So the question will be like, okay, how about if I leave the magnet stationary but move the loop toward the magnet? Well, you're going to get the same thing. All right. So that's why it's a relative motion between magnet and the coil. If they're moving toward each other or away from each other, or one is moving toward each other and things like that, you're going to get induced current in that coil. Again, remember, that coil is not connected to anything. So technically, if I put some kind of light bulb here, right, that light bulb will be, shining right now because there is a current running through that, right? So this current is going to go through the light bulb, and the light bulb will be, bright. Okay, that means you generate a current. How do you generate the current? By moving the magnet, using the magnetic field. All right, so that means he more or less was successful in generating electricity from magnetic fields. But there are some other experiments, we're going to be able to see. So let's say, all right, so current exists in the wire even though no batteries are connected to the wire. Okay, so I think we have established that right now. All right, so we call this an induced current, right? That means this is an induced current, which means, again, this current is induced due to that magnetic field from that. Remember, this is external magnetic field, right? So some kind of external magnetic field. And this external magnetic field induces, so sometimes I just put like IN, induced current, for, indicating that it's induced current. Obviously, if there's a current, that was due to the, potential difference between negative and positive terminals. So we can say that in this case, this one becomes positive, this one becomes negative, right? But then we can say that, there's an EMF, right? Remember, EMF means that, there's a two different potential between positive, negative, ends of a wire, and it drives the current. That means the current here is due to that induced EMF. So that's why we call such current as induced current, and it is produced by induced EMF. In a way, you can say that when you are moving the magnet, it generates or produces potential difference between the ends of the conductor, and there is a EMF established, which basically then drives the current. All right, so some of his next experiments then involve the second source of magnetic field. Remember, so second source is a current running through a wire. Okay, that means what he has here is, so this is still, see, this is the coil, right? This is the coil that is not connected to anything, so it's just connected to the ammeter. And then we have another one. Let's call this primary coil. Okay, so the primary coil is just another conductor, but it is connected to the battery. It is connected to the battery. Okay, to maximize our effect a little bit, right? We wrap those around, this iron core. So, and that's going to give us basically a little bit, stronger magnetic field, better effect. Okay. But the idea here is this. So you have the primary coil, which if we close the switch, there is a current running. So there's going to be current like this. This is not the induced current. This is the current, in the primary coil due to the battery, right? So this is just like, you can think of like a regular DC circuit. Okay. But of course, we learned that if there's a current running through a conductor, okay, there's going to be a magnetic field. Okay. So then secondary coil, which again also wrapped around that iron ring, right, is now going to have magnetic. So magnetic field's basically going to be going through here, right? There's going to be magnetic field inside that iron ring, right? Through the center of that, secondary coil. Okay. Again, there is no battery in the secondary coil, and it is not electrically connected to the primary coil. Okay, they're not electrically connected. So you are basically, only kind of connecting them in a way that the magnetic field generated by primary coil will be going through the center of the secondary coil. Okay, so At the instant the switch is closed, the galvanometer, the ammeter, right, needle deflects in one direction and then return to zero. Okay. Now, what it means is that the induced current was detected in the secondary coil. But again, so it deflects in one direction and then returns to zero. Okay, it doesn't stay there. It returns to zero very quickly, but it detects, like, let's say, for a fraction of a second. Okay, now what's going on over there? Well, remember, so let's say we go ahead and open the switch, and let's say if you open the switch for the primary coil, there is no current. Okay, now when I close the switch, then this current here, this doesn't go and at t equals 0 becomes its maximum. What it does here, it slowly increases. Well, I mean, when I say slowly, it's so the current over time this is for the primary. So the current over time, it happens maybe in milliseconds, okay? So for us, it's very quickly. We're not gonna see any difference. But for ammeter, is long enough that it can, see that there is a increase in current as a function of time until it reaches its maximum value. Remember, since magnetic field generated by the primary coil, right, is proportional to the current in the primary coil, okay, then this magnetic field through the secondary coil, remember, this is the magnetic field going through the secondary coil, right? Also, as the current increases, magnetic field increases, okay? Well, that means magnetic field strength through the secondary coil, at least for that fraction of a second, goes from 0 to its maximum value. And then current is induced, because at that instant, or at that, for that fraction of a second, or maybe like a second or so, right, the magnetic field through that secondary coil is changing, and there is an induced current. But as the primary coil current goes to its maximum, so it stops changing, then magnetic field stops changing, and then magnetic field basically becomes constant and uniform. As soon as the magnetic field becomes constant and uniform and no longer changing, induced current returns to 0. That's what happens there. Okay. Again, that might happen within a fraction of a second, or maybe like in 1 or 2 seconds, right? But it's noticeable and detectable with that sensitive ammeter. All right. So one thing we can do here is, let's say, all right, so now we have a steady current in the primary coil. That means the magnetic field is steady in the secondary coil, and the induced current is 0. Okay, if you wait a long time, that means all of those values are steady and the induced current is 0. Now what we're gonna do here, we're gonna open the switch. And as we open the switch, you can see, right, then galvanometer needle deflects in the opposite direction, but then again returns to 0. Now what happens here? Well, what happens here is that now you have a steady current, so steady magnetic field. But as you open the switch, current decreases. Again, it doesn't decrease instantaneously. It decreases as a function of time. And the magnetic field decreases. Again, it doesn't happen instantaneously. It takes maybe like let's say a second. Okay. But that 1 second is enough for the current to be induced in the secondary coil, because during that 1 second, the magnetic field through the center of the secondary coil is decreasing. As it is decreasing, there is an induced current. Okay, so there is an induced current in the secondary coil. All right, that means the galvanometer reads 0 when there is a steady current, or when there is no current in the primary circuit. Okay, and only shows induced current when there is changing current, either increasing to its maximum or decreasing from its maximum to 0, right? But there's a changing current which generates changing magnetic field through the secondary coil. All right. So the ammeter deflect when the magnet is moving toward or away from the loop, that was that first setup. And then the ammeter also deflects when the loop is moved toward or away from the magnet. By the way, this also I talked about, right? That is also for the first setup. That means it doesn't matter if you move the magnet toward the loop or you move the loop toward the magnet. There's a relative motion between those two, right? And then electric current is set up in the coil as long as the relative motion occurs between the magnet and the coil. That means that, loop of wire can have electric current, as long as you keep moving the magnet relative to that, coil of wire. If you move the magnet out, back and forth, like forever, right? There's going to be a current there. You stop, the current goes to zero. Okay, and we're talking about this is induced current, right? So this is induced current that is produced by an induced EMF, and induced EMF is produced by the moving magnet. Okay, by the fact that the magnet is moving. Okay. Now, one of the things we're going to look at in the next few slides is the concept of magnetic flux. Well, we are, familiar with the concept of flux. If you remember, there was a, electric flux, right? The Gauss's law, where we used integral of E dot dA to be that magnetic flux, electric flux, right? Remember that was electric flux, which represent, like, let's say you choose an area of interest and look at electric field lines going through that area. Okay, so, and remember what we did? We chose a vector A, right? So this was electric field, and we chose a vector dA, and we did the dot product between those two, okay? And then we had this. Similar idea we're gonna do for the magnetic flux, where we have some kind of, this is our, let's say the entire system, but what I want to do here is just choose a small, remember A here is the entire area, but I'm choosing just a small dA, which is just a small area over there. So dA is the area of that, tiny small element, okay? So remember, dA is a vector perpendicular to that surface of interest. And let's say then magnetic field is, if it's going through that area, and then you have an angle theta that, is, let's say, less than 90 degrees. That means the angle between dA and B here is less than 90 degrees. Then we can, again, assume that, there are some field lines going through the area. Remember, this electric flux was non-zero as long as we can see that some of the field lines going through that area. Same thing is here. So if you have a field lines going through some area A, then we can calculate the flux, and the flux depends on the magnetic field and the area. Okay, remember, so the dot product was, let's say, A dot B, dot product between any two vectors, is equals to then A B cosine of, let's say cosine of phi, if you want to call that, right? Cosine of phi. Remember, this is a dot product between any two vectors. And you have, right, you have one vector, you have two vectors, and then you have a dot product, okay? But obviously, like, let's say if you want to generalize for the entire thing, we're going to have to, eventually integrate, okay? So magnetic flux, then just like electric flux, you can see, right, is then B dot dA. Okay, so they have exactly same format. One is for the electric field, one is for the magnetic field. Okay, so one thing we have though is the magnetic field, or magnetic flux. I'm put it like the magnetic flux has a unit of Tesla times meter square, but we define that to be a Weber. Okay, so Weber is a unit for the magnetic flux. Well, electric flux didn't have a defined unit, so it was just Newton per Coulomb times meter square. So just in terms of the electric field and area. But magnetic flux, we just call that Weber, and it just represents how many of those field lines, basically, how many of those magnetic field lines going through that area of interest. Right, so think like this, because what I have here is if the magnetic flux is constant, so if the magnetic field is constant, so I can write this as BdA, okay? Or we can say BdA cosine of phi, which is the angle between them. If the B is constant, I remove that. And I can even, remove the cosine of, phi angle between them, because let's say, this angle doesn't change, or, theta or phi doesn't matter, right? And you just have in terms of just dA, okay? And if you integrate that, so it becomes B integral of dA, just A, and then that gives you cosine of phi, okay? That means this is the equation for the magnetic flux if the magnetic field is uniform, okay? If the magnetic field is uniform to that area, then you have done BA cosine of phi, okay? Remember, this dot product, right? So this will be 0 if phi here is 90 degrees, okay? And it will be maximum if phi here is 0 degrees, okay? That means if the magnetic field had, let's say, this orientation, then you would get maximum flux instead of, let's say, oriented with some angle theta. All right. Now, then what we have here is, you can see, right, in a way, this concept of flux is relatively useful because remember that loop that we consider, right? So that loop, you know, connected to the ammeter. Okay. So see, if you have a magnetic field lines going through that, you know, center of the loop, then you can choose the area of the loop, and then you can look at, you know, the magnetic field lines going through that loop, and you can calculate the flux, which will be BA cosine of phi. Okay, so it will be BA cosine of phi. Well, see, this will be magnetic flux at some instant. So let's say, for example, this will be at t equals 0. So what is the magnetic field strength to the loop? That's B. Area A, that's A, and their orientation, cosine of phi, then I can calculate the flux. Okay. Well, maybe a little bit later on, if the magnetic source is moving, right, then you can see, right, so magnetic source getting closer, that means magnetic strength inside increases. Then I can calculate magnetic flux a little bit later. So it will be, let's say, B prime, A prime cosine of phi. And then if, you know, some of those things changes, right? So you can see, right, you can change the flux by changing magnetic field or changing area or the orientation. If any of those things changes, right, that means you basically have changing flux. So let's say, for example, if you have a magnet that is moving, right, toward, then magnetic flux will be changing, right? Because B is changing. And as a function of time, you can say then flux is changing. So that's why, in a way, one of the things we can do here is when we are setting up this Faraday's law of induction, we can look at it in terms of then changing flux. That means when those, you know, remember that induced current and induced EMF was due to the moving, you know, magnetic source, which changed the magnetic field strength inside. We can say that it happens because the magnetic flux inside is changing. All right, so again, so an EMF is induced in a circuit when the magnetic flux through the surface bounded by the circuit changes with time. Okay, that means if the magnetic flux changes, you can assume that, you know, it can be due to the magnetic field change through that let's say, surface. All right, and the general statement of this result is Faraday's law of induction. That means the EMF induced in a circuit is equal to the time rate of change of magnetic flux through the circuit. So let's say when this happens, right, when you have a moving, let's say, moving magnetic source relative to the to your loop, right, or basically if you have an induced EMF, an induced current, is because you can say that there is a change in flux, right, as a function of time. And that equation basically gives you this induced EMF, which is induced EMF equals, you can see, right, the rate of change, which means that, you know, d flux dt, change in flux is a function of time. Okay. So that's kind of, you know, what we have. And this negative generally represent that when, you know, when flux is increasing, EMF is negative. When flux is decreasing, EMF is positive. So that's why you have two different direction for the current, right? So the current, you know, changes direction depending if the, you know, magnet is moving toward or away. That means you can conclude that there is a, you know, contribution, right, of changing current due to the relative motion of the magnet. Okay. Anyway, so the important thing here is, if I, let's say, write down this is induced, I like to do that. So the induced EMF is due to the change in flux through that surface. Okay. That means whenever you have a change in flux, and remember, flux, right? So in a way, I can write this like this. So ddt, and this is BA cosine of phi. And you can see that you have a change in flux, you know, in terms of those either magnetic field or area or the orientation between them. All right. So you can say the flux through the surface bounded by the circuit. Okay. That means bounded by that loop. You're only considering the center of that loop. Now, you might have a loop that has more than one turn. Okay, so like a solenoid over there, it can be like, 5, 10, 100,000, right? And you can kind of incorporate that, right? Because what you have here is increasing the number of the loops or number of turns in your conductor, right? It actually increases the EMF. You can see, right, it's directly proportional to that. So that means more general equation will be to put that n over there. So if you have a if your loop has an n equals 1, then just basically n is 1. If you have 10, then just plug in 10, and you can see, right, it directly changes the amount of EMF, which directly changes the amount value of the current. Okay, so you can see because the loops are in series, so the EMFs in the individual loops adds to give the total EMF. All right, so this is kind of how to use this equation, because for example, let's say you have that area of interest and there is a magnetic field going through that area, and you can see, right, so this is the normal. So in a way you can say that this is the normal, A vector A, right? And so you have this angle theta between them. And if you want to calculate magnetic flux, you're going to have to do integral of B dot dA. So this is, remember, this is the general equation for the magnetic flux. And magnetic field, since you can see from the diagram, is uniform, it can, first you change it to B dA cosine theta, because you assume that this guy doesn't change, right? And, that means orientation of B and dA doesn't change. And then you can remove B cosine theta from the integral, right? And then becomes the integral of dA, which is BA cosine theta, which is, an equation that I already derived for you. That means you can see that magnetic flux is just BA cosine theta. And then when you're looking at the induced EMF, right? So it's negative d dt, BA cosine theta. Okay, so let's say, for example, if, in this particular, let's say case, let's say over here, I start changing the magnetic field strength, then what you can see here is this becomes negative dB dt, then A cosine of theta. Let's say I don't change the shape of that loop, I don't change the orientation of the magnetic field and area, but let's say if I'm changing the magnetic field strength as a function of time, then I get that. So that means EMF will be equals to negative A cosine of theta. Those things are more or less constant, but then dB dt. So I might have to, let's say, take the derivative of B or something like that if I'm given it how it changes as a function of time. All right, so EMF can be induced in a circuit by changing the magnetic flux in several ways. You kind of summarize all this. So the magnitude of the field can vary with time. Okay, that means my equation, right? So this change in flux over time can be due to change in magnetic field over time, and everything else remains constant. Or I can change the area of the circuit. That means this change in flux over time is due to the change in area over time, where B and cosine of phi then becomes constant. Or I can change the angle. That means what I can do here is, let's say I have this orientation with this magnetic field. Maybe then I can change the orientation, where here's the vector dA, and then you can see where the magnetic field. So I'm changing the orientation. So then you have then this d cosine of theta as a function of time. So I can have that. Okay. All right, so that means there, you can have individually 1, 2, 3, or any combination of this to occur. Okay, that means any of those changes will change the flux, or any of the multiple changes. Obviously, if you have multiple things, then obviously flux changes even more. But those are the things that can induce EMF and induce current. All right, so let's look at a few examples here. So in a physics laboratory experiment, a coil with 200 turns enclosing an area of 12 centimeters square is rotated in 0.04 seconds from a position where its plane is perpendicular to the Earth's magnetic field to a position where its plane is parallel to the magnetic field. Okay, and the Earth's magnetic field at the lab location is 6 times 10 to the negative 5 Tesla. Right. So what is the total magnetic flux through the coil before it is rotated? And what is it after it is rotated? and what is the average EMF induced in the coil. All right, so let's look at sort of like a simple diagram. So let's say this is the magnetic field. Okay, so let's say this is the magnetic field. Okay, so then what I get here is this. So let's say this was then my loop. First, it says its position is such that the plane, its plane, is perpendicular to Earth's magnetic field. That means you maybe have a coil like that. See, what its plane is perpendicular to magnetic field, which means in a way, if I draw this vector A, or in this case I can do A, not necessarily dA, so I can say vector A, or let me do it, the dA, why not, same thing, right? A or dA, same thing. So you can see, right, then, angle theta or phi, whatever here is 0 degrees, okay? 0 degrees. And then what I do here is I can use this to calculate the magnetic flux, which is integral of B dot dA, or integral of B dA cosine of theta. All right. So magnetic field, since it's Earth, it doesn't change, it's constant. Orientation at that instant, I can say it's a cosine of, it's 0 degrees, so I can technically ignore it, right? Because this is equals to 1. Then it becomes B, then integral of dA. Okay. And this is just going to give me B times A. All right, so if I integrate, I'm going to just get B times A. All right, so then what is the flux? Well, B here is 6 times 10 to the negative 5 Tesla times then 12 centimeters square. I can't use that. What I need to do here is to convert that, where then 100 centimeters is 1 meter, and then square that as well, right? And we should get 7.2 times 10 to the negative 8 Weber. Okay, so that's my magnetic flux. Then what I do here is I change the orientation to like this. Okay, so then this is my plane, where then what I have here is magnetic field, then going to be like that, right? So it doesn't change, magnetic field, direction doesn't change, but I change my orientation from the plane of that, a coil that was perpendicular to the field, or then, theta was 0 degrees because of the dA. Now my dA is pointing in this direction, right? Remember, dA always perpendicular to the surface. That's my dA, that's my B. So when I'm calculating, then think like this. This was my, initial, and this will be my final flux. Okay, so this will be then integral of B dot dA. And remember, this is a dot product between two perpendicular vectors. You get 0. Right, remember, dot product between any two perpendicular vectors, you get 0. All right, that was part A. Part B says, then what is the average EMF induced in the coil? Well, average EMF is basically that same equation, Faraday's law, right? So if you do like a negative n times change in flux over time, like this, right? So remember, if you're using this equation, this is instantaneous. But if you change that d phi dt into the delta flux, delta t, then this becomes average. All right, so let's do this. Let's take absolute value, because we just want to find the value, right? And this will be then 200 turns, then times change in flux, which is final, which is 0, minus initial, which is 7.2 times 10 to the negative 8 Weber. And this is over the time interval, which we're given as 0.04 seconds. All right. Okay, so if I calculate this, I'm going to get roughly 3.6 times 10 to the negative 4 volts, which means my average EMF is 0.36 millivolts. There you go. All right, here's one more example. So we have a straight current carrying wire. So this guy here is straight wire, straight conductor with the current running through that. Okay, and then we have a rectangular loop next to that. Okay, So what we want to do here is we want to, part A, compute the magnetic flux through the rectangular loop. All right, so the question is there flux even in the first place? Well, remember this wire, the straight wire, if it has a current running through that, it generates, magnetic field that loops around it, right? That means the magnetic field gonna go like this, where anywhere inside this rectangular loop, magnetic field, if you use your right-hand rule, you will see, right, it's basically gonna be, in this direction, which is into the page. It's going to be into the page. That means all that region to the right of the straight wire is into the page, but I'm only interested inside that rectangular loop. So I can ignore everything else and I say, okay, so the magnetic field inside the rectangular loop is into the page. Well, I have magnetic field and I have technically, if I do the vector A, I can see, right, I can take a vector and also, will be into the page, right? This will be vector A, or dA if you want to call that, right? So, but one of the things I have here is, well, my area, not necessarily area, but let's say you can see, right? So my dA is basically changing, right? So let's say, what I have here is as a function of, position, right? My, area pretty much changes. Okay. That means what I have here is, going from here, you can see, right, my position is changing, right? So let's say if I consider this strip, it has this area, then the next one and the next one, and every time I go to the right, my area starts changing, okay? That means what I have here is this. So I can look at in terms of my flux. So let's say magnetic flux, right? Which is equals to, BDA, but because of that, right, because of the, what I have here is I have a position change, right, going from this D, and then I have, it changes from D to, let's say being D distance from the wire to D plus A distance from the wire. When I'm looking at, let's say just one of the strips. So let's say I'm looking at maybe one that is right here. And I'm saying that this has a distance, basically X, right? This has a distance X from the straight wire. And I'm going to then set up my equation in terms of that. So I'm going to find the contribution of the flux for that small strip, and then, expand all the way to the, let's say from one end to the other. Okay. That means this is equals to the magnetic field through that small strip that has an area of, let's say, dA. Okay. And what we do here is we can see that, right? So then dA is equals to, length times, length times the width, right? But what I have here is my B here is, right? So this part doesn't change. As you go along this B line, right, it always has the same distance. But as you go along the A, the distance with respect to the wire changes all the way until it's equals A plus B. That means dA here is equals to B, which is constant, then times dx. Okay. So that means dA here is basically becomes ddx. And remember, if I want to find then the magnetic field at the position of that strip, right, according to the Biot-Savart law, that equation was mu naught times the current divided by 2 pi times x. Okay, so 2 pi times x. That's the magnetic field, that we derived in the last chapter. Okay. Then what I can do here is this. I can say then the small element flux is equals to, so you can say, right, it's magnetic field times dA, but magnetic field is mu naught I over 2 pi x, okay? And my area here is B dx, okay? Then what I do here is I integrate both sides. The left side here, integral of dB becomes just flux, okay? On the right side, then I have all this inside the integral. All right, so, but I can see here is that mu naught is a constant, current is a constant, 2 pi is a constant, B is a constant. The only thing here is, dx over x. Okay. And I'm going to integrate from distance because my rectangular loop has a closest distance of d, and the furthest distance is d plus a. Okay. Well, it's a simple integral, right? It's basically ln x. So we get that mu naught times current times b divided by 2 pi. And then here we get ln, upper limit d plus a over the lower, which is d. Okay. So this is then the flux. And the next thing what we do here is I just plug in all the values, right? So I have then mu naught times the current, which is for part B, is given that take A equals 5 centimeters, B equals 10 centimeters, D equals 2 centimeters, and current equals 20 amps. So we plug in those values, right? So B is 0.1 meters, then this guy, then 2 pi, then we have ln. And then here, I don't even have to convert things into, meters because, it's a ratio, it's going to cancel out. So D is 2 plus A is 5 divided by B, which is 10, right? And, they're going to cancel out. And I'm going to get 0.5 microweber. And that's my, the last answer. All right, so let's consider now the next concept, which is called emotional EMF. All right, so what we're doing here is we're actually going to see that if you have some kind of conductor that is moving in an external magnetic field, it is possible that this conductor can be, used as a source of EMF. Okay, that means you can have this, to generate, electricity. Remember, EMF is as a source that can drive current and, basically gives you electricity. One thing we learned that, one of the sources of EMF is the battery or power supply, right? But here we're going to see that it's possible that, you can get similar thing with a moving conductor in a magnetic field. All right, so we're going to consider a straight metal conductor in a uniform magnetic field. So one thing we can see here is this. If there is a magnetic field into the page, right? So there's a magnetic field into the page, and this conductor is moving to the right. One thing we can do here, remember, this conductor has a lot of charges, right? There's going to be a lot of negative charges, those free electrons, right, in the conductor. If you use your right-hand rule, your fingers in the direction of the velocity, you curl in the direction of the magnetic field, you're going to see that there is going to be an upward force on all of the positive charges and downward force on all of the negative charges. That means those negative charges can have a force acting on them that is going to be downward, okay? And that means, if this conductor moving to the right in a magnetic field that is into the page, there is a force acting on it that is to the right. The force acting that is down on a negative charge and up on a positive charge. And those charges then going to be then pushed in opposite direction of the conductor. Then eventually you're going to get, all the negative ones right here and all the positive ones right here, okay? So you're going to get a separation of charges. And, and that's very important. So the force on electrons down, you can remember this right-hand rule. And whenever you get that, think like this, you have then all of the positive, all of the negative, right? And you can actually have a current running, okay? So that's the interesting thing about this. All right, so again, this is known as emotional EMF. So it's the one that is one induced in a conductor moving through a magnetic field. That means important thing here is to have a moving, conductor. And as soon as you get that, right, you can see, right, if you have a conductor moving to the right, then those forces, right, electric force is going to be magnetic force is going to be pushing all the positive charges up, all the negative charges down, right? And you get kind of separation, okay? And let's assume this L is the length of the conductor, okay? So then what you get here is this. So the force acting on it, remember, it's a magnetic force. It's QV cross B, right? So, this magnetic force. So the Q here is the, charges inside that conductor. V here is the velocity of the conductor. And B here is the magnetic field strength. That means this is, what we have seen before, right? In chapter 22, which is there's a magnetic force on all of those charges. So we're talking about like inside the conductor, every single charge has that, force acting on it. And the force has that strength. All right, so now what we get here is this. There's also an electric field produced. So if I kind of, show you guys here, so see there's this conductor, right? So once there's separation, right? Once there's separation, so what you get here is, something like this. There's an upward magnetic force on a positive charges, right? And there's going to be also an electric force. Sorry, this is actually then, let's say, an electric force. Okay, and there's going to be a magnetic force like this. Okay, like over here in this diagram. Okay, and there's going to be an electric field, and there's going to be a magnetic field. Okay, and eventually they're going to cancel each other. Remember, there's an electric force which is Q times E. Okay, and then what you're going to get here is QE minus, sorry, FE minus FB, which is going to be equals 0. Remember, this will mean that Q times E equals to QVB. You cancel the Q's, and you can see, right, E equals V times B. Okay, so we kind of use the similar idea in a velocity selector in the last chapter. But one of the things we get here inside the conductor is that as the charges start separating, there's an electric field. As there's an electric field, there's also electric force. Okay, electric force pushes those charges up. The other ones go basically down, right? And you get, pretty much this potential difference, right? That will be, between those two ends. So electric field produced in the conductor is uniform, right? And is related to the potential difference across the ends of the conductor. And if you remember, right, there was this equation where delta V was equal to the negative of integral E dot dl. So this was the general equation. But if the electric field is uniform, we can, take that out of the integral and calculate and end up with just E times L. Then delta V is equals to E times L. This was, again, something we learned in chapter 20. Okay. Now, what we get from here is I just showed you that E was V times B, right, from the previous slide. So then I replace this with that, and that means you can also have delta V equals B times L times B. That means if you have a motional EMF, then potential difference of that motional EMF will be proportional to the magnetic strength. Remember, that was the external magnetic field, length of the conductor, and how fast the conductor is moving. Right, so the upper end is at the higher potential than the lower end, and the potential difference is maintained as long as the conductor is moving through the magnetic field. As soon as it starts, delta V is 0 because velocity is 0, for example, right? So it depends on the moving conductor. All right, so if the motion is reversed, the polarity of delta V is also reversed. That means, for example, if the conductor is moving to the left, then you're going to get forces in opposite direction, and you get the polarity different. That means the positive one is going to be accumulated at the bottom, negative one is going to be accumulated at the top. Okay. All right. So one thing we can do here is we can put this conductor, right, in a closed circuit like this. That means we have sort of like a U-shaped rails like this, where there's some resistor here. So these are, another conductors of negligible resistance. And what we have here is there's connected to some kind of resistor like this. And this moving rod is pretty much completes a circuit for us. And assume that the bar has 0 resistance. Those, basically those bars have 0 resistance, and including our, let's say our moving conductor. So if I do that, right, if I move this rod to the right, remember, we will end up this, the top region to be positive, the bottom will be all negative, right? Because all the positives one going to be pushed up, all the negative one going to be pulled down, and then you end up as this acts like a battery with positive terminal and negative terminal, and that will be a current running in this direction. In this case, counterclockwise in the circuit. Obviously, if you have the conductor moving to the left, then there will be current clockwise in the same region. All right. So the flux is, remember, B times A, and A here is the, the length times this distance x, right? So the x here is the distance of the, moving conductor relative to the other end of the, let's say, my circuit, right? So then this x. And one of the things we can see here is, this is basically B times A, and A is given as in terms of length times x. Okay, so that's basically my flux. Okay, flux in the circuit. All right, so now you can see that there will be an induced EMF because what I have here is this flux, right? So the flux that I have, which is B times L times X, will be changing. Remember, as that conductor, let's say, moving to the right, well, X will be increasing, which means the, flux is increasing. If the conductor moving to the left, X is decreasing, flux is decreasing. But in any case, there is a, change in flux. And we learned if there's a change in flux, there is then, induced EMF. And you can see, right, induced EMF here is given in terms of Faraday's law, which is negative change in flux, derivative of change in flux over time, right? The derivative of the flux over time. And now what we can say here is that this is a negative d dt of the flux, which is BLX. Okay. And what we get here is then negative B and L are constant, so I can remove them. And then this becomes dx dt. Okay. And obviously we know that, dx dt is nothing but, a velocity. That means EMF is equals to BLV, right? So it's equals to B times L times V, which we kind of already derived, looked at, in terms of potential difference between the ends. That means the EMF that is generated, right, has also the same, a value or same magnitude, which is B times L times V. Okay, that means that's why it depends on the magnetic field strength, the length of the conductor, and the speed or the velocity of the, let's say, the movable bar. Okay. Then how can we then, for example, find that induced current? Well, remember, if there's a resistor there of known resistance, then we can, basically use that, right? We can say, all right, so then the current here is EMF divided by the resistance. So we can put absolute value because remember, again, there's no such thing as negative, current or, remember the direction, the negative positive just give you clockwise, counterclockwise, but, you can put absolute value and calculate what is the, the current value. All right, so then it will be then BLV divided by R, right? So you plug in that and you, calculate. All right, that means this moving conductor in a magnetic field, can easily be modeled as just a regular, closed circuit, but as long as it's moving, because as soon as it starts moving, then you can see, right, V0 means that, current zero. As soon as you have V0, the current is zero, okay? So that's why EMF is zero and current is zero as soon as you stop moving the conductor. All right. In terms of then from the energy point of view, right? So remember what we have here is the applied force that, when you take the bar and you move it to the right, well, you're doing work, right? So it does work on the conductor, okay? And that this moves the charge through the magnetic field, okay? And then the change in energy of the system during some time interval must be equal to the transfer of energy into the system by work, okay? That means when we are, doing work by moving the conductor, we're transferring energy into the system, which is in the energy in the circuit, right? And when we do that, that means how much energy the system gains that, later will be, let's say, dissipated by the resistor, right? Should be equal to one another. That means if I find how much energy is transferred into the system, right? So let's say the power input, which will be given, for example, as the force they apply times the velocity of the bar, okay? So this is then is equals to, remember, this is the force acting on already, there's a current running. So this is the force that I can write in terms of ILB, force on a wire, right? And then times V, okay? And here then I can rewrite this as we just learned, right? That the current here is VLV over the resistance, that's my current, then times, L, so LB times another V. So in a way, what we get here is this. So we get B square, L square, V square over R. Okay. B square, L square, V square over R. Okay. And one of the things, if I do this, for example, right, if I take it and, just multiply by R over R, which is just 1, right? If I just do that, one of the things I can see here is this will be, equally equals to, because then what I can get here is, see, BLV. So if I take this one and move it there, so it makes this guy here square, and then R, right, like that. And that's nothing but the current square times R. And that was the power of the energy dissipated by the resistor that we learned in the, chapter 20, chapter 21, which was, let's say that power dissipated by a resistor, you can find by current square times the resistance. So that's why how much energy you input by pushing the rod is equals to exactly by the energy dissipated by the resistor in your system. All right, so let's look at this example here. All right, so we have the circuit where there is the external magnetic field strength of 0.8 Tesla, the rod speed of 10 meters per second, and it has a length of 20 centimeters. There's also a resistor of 2 ohms. Okay, and everything else has a negligible resistance. We want to find the induced EMF in the circuit, induced current in the circuit, and the magnetic and the force needed to move the rod with constant speed. So let's do that, and then you will go to the last part. All right, so here's then what we get. So the EMF induced is, should be simple enough because it's B times L times V. Okay, so 0.8 Tesla times 0.2 meters and times 10 meters per second. And that should give me 1.6 volts. So that's how much induced EMF I will get. That's part A. Part B, induced current. Well, induced current is equals to, the EMF over the resistance. So 1.6 volts divided by 2 ohms. So 0.8 amps. So those two should be easy enough. The last one said, the part C says the force needed to move the rod with constant speed. All right. That means we want to look at what force moves it with constant speed. All right. So here, if you remember, right, so if I'm pushing this guy, I'm applying force. At the same time, because there's a current in the conductor, and there's a current in the conductor with length L, and there's an into the page magnetic field, use your right hand rule. You can see, right, your fingers up in the direction of the current. You curl in the direction, into the page, into the magnetic field. You can see, right, that there is a magnetic force acting on that, movable conductor that is to the left. That means what I have here is that applied force to the right minus magnetic force to the left. And we assume that, when we push, we're not making it accelerate. We're just making it move at constant speed. So this is equals to 0. That means applied force is technically equal to the magnetic force. Okay, and magnetic force was I times L times B. Okay, that means I can calculate, this applied force from the magnetic force, and this is current 0.8 amps times the length 0.2 meters times the magnetic field strength, which is 0.8 Tesla. All right, so we're going to get 0.13 newtons for that applied force. All right, and part D here, it says the power delivered by the force, and part 3 says what is the rate of joule heating in the resistor. Well, D here is power delivered by the force, which is F times V. So 0.13 newtons times 10 meters per second. So we get 1.3 watts. And for part E is the power or rate of joule heating, which means I will just want to find power, right? Rate of energy, dissipation, which we can do I squared times the resistance. So 0.8 amps square times resistance of 2 ohms. And we should get here is 1.3 watts, just like before, because as we said, right, energy delivered is same as energy dissipated, in our circuit. All right. All right, so the next we're going to talk about Lenz's law. Okay, so the Lenz's law is a conceptual description of the direction of the the induced current and induced EMF. They're always pretty much going to be same kind, like same direction, for example. So the idea here is Faraday's law gives you the mathematical way of looking at calculating the induced EMF. But sometimes it's confusing to like, okay, in which direction is the induced current? Well, the Lenz's law allows you to get that from a very simple, let's say, conceptual, kind of like visualize the look at the system, right? Visualize what's going on, and from that you can derive the direction of the current, pretty much conceptually. All right, so what we do here is you can see, right, the Faraday's law indicates that induced EMF and the change in flux have opposite signs. Remember, we have that negative sign, right, in terms of EMF and the change in flux. All right, so when a change occurs in the magnetic flux, the direction of the induced EMF and induced current can be found from this Lenz's law. Okay. All right, so the idea for this, right, so the idea for the Lenz's law is that it always gonna try to, let's say, oppose the change in your system, let's say. So I'm gonna give you like a few examples. So for example, let's say you have a loop, basically circular loop of wire, okay? And then there is a, let's say, magnetic field, upward magnetic field. So this is external magnetic field, right? So this is a magnetic field generated by some external source. Okay. Now, what we get here is this. This is kind of like similar to the very first experiment, right? So if you have a loop and there's a magnetic field, remember, I can find the flux, right? So I can find the flux, which is, BA in this case, because, this is my, let's say DA, right? So becomes B times A, and it's, here's the magnetic flux. It's a non-zero flux. But if the magnetic field is constant and uniform and non-changing, so this is magnetic flux initially, magnetic flux later is still B times A. And then if I'm doing the induced EMF, which is negative change in flux over time, I'm going to get 0 because flux is not changing. Okay. Now, that means in order for there to be induced EMF, there has to be a, let's say, change in flux. So how do we change in flux? Well, one way we can change flux is by changing magnetic field strength. So for example, now I change the magnetic field strength. That means, let's say, for example, I start increasing it by a certain value of dB, right? So I'm changing that as a function of time. That means the magnetic field through that loop starts increasing. Well, if it's increasing, that means my, what I get here is the, I'm going to get change in flux, right, over time, which will be, dB dt times A, let's say. A doesn't change, but for example, dB dt, right, magnetic field is changing. Okay, so I will get change in flux, which means that now if I'm doing EMF, I'm going to get, let's say, change in flux over time, and this is no longer zero. No longer zero because I do have a change in flux due to the change in magnetic field strength. Okay. Now, what happens here is then the loop does not like the change and is going to try to basically fight it. Okay. So then what is it going to try to do? Well, it's going to try to put the or just basically change the flux back to its original value. That means flux is increasing, so its goal will be to decrease the flux, right? So if it can decrease the flux, so it will go back to the same, let's say, original value. You can think like sort of like an equilibrium, right? So you're changing the equilibrium, right? And it's trying to fight it. So then how can we change? How can this loop change the flux? Well, remember, what we're doing here is we are increasing the magnetic field, right? So we're increasing the flux. The loop can try to decrease the flux. And one way it can try to decrease, remember, the magnetic field right now is increasing by that much as every second. So what if the loop generates its own magnetic field? There is going to be in the opposite direction, let's say dB induced, right? That, going to be then this magnetic field that is induced by the loop will fight the increase in magnetic field due to external source. And those, let's say, can eliminate each other, and then the flux is the same as before. All right, so, and that's what the loop gonna try to do. It's gonna try to oppose the change. So, okay, so you're increasing magnetic field upward, it's gonna try to pump magnetic field downward. How can it do that? Well, remember, if there is, for example, right, if there was a clockwise current in the circuit, right, for example, so if it would generate, see, a clockwise current in the loop, we learned that, right, in the last chapter, that clockwise current in the loop will have a magnetic field downward through the loop. That means this loop can generate its own magnetic field to try to fight the change in the external magnetic field. So it's gonna create current. In this case, it has to generate magnetic field down because it's gonna oppose increase in magnetic field. That means magnetic field induced should be in the opposite direction of the external magnetic field. And in order to have a downward induced magnetic field in the loop, we should have a clockwise current. So that's why the current here has to be clockwise, because the induced magnetic field has to be in the opposite direction of the external magnetic field, because it's going to try to decrease the the value of the flux, right? And you can easily then say that Lenz's law allows you to see this and say, all right, so now the EMF is let's say also going to be in the same direction, right? So that's why you can see, right, EMF here has to be negative. Why is EMF negative? Because my the current here is clockwise, and remember, clockwise is technically negative, right? Counterclockwise would be positive. So if I come back to this equation, you can see, right, my change in flux over time due to the external source is positive because my flux is increasing. And EMF has to be negative, so that's why we have that negative sign. So if this guy here is positive, EMF then will be negative, right? EMF will be negative. And we can see that from the Lenz's law. EMF is in the same direction as the current because current has to be clockwise because it needs induced magnetic field downward, all right? So let's look at, let's say, for example, what would happen if then we still have the same loop, and let's say we still have the same magnetic field, okay? But this time we're gonna get magnetic field that is gonna be decreasing, okay? That means, for example, magnetic field is decreasing, which means that it's, it's less than before, right? So this is gonna be my B prime. It's less than before. So it's gonna start decreasing as a function of time. Okay, so it's gonna, decrease as a function of time. Okay, or you can say, right, so if I'm looking at the, change, the change will be, down, right? So it's gonna be negative because smaller value minus bigger value gonna give you negative. So in a way that this is my B prime, okay, or my DB prime, something like that. Okay, that means magnetic, external magnetic field is decreasing and change is basically negative in this case. So again, flux is changing. So the flux is changing because magnetic field is changing. In this case, flux is decreasing, right? Because magnetic field is decreasing. So what can loop then do to fight this change? Well, remember, if the flux is decreasing, maybe it can try to increase the flux on its own. And how can it do that? Maybe it can pump magnetic field, induce magnetic field, right, in the same direction as, let's say, the original magnetic field, right? That means, all right, so you're decreasing, well, I'm going to pump more magnetic field in the same direction to increase it, or basically eliminate that change, right? And in that case, you know, again, it's fighting, right? It's trying to reinforce magnetic field now. It has to be induced magnetic field in the direction of the external magnetic field. In order for us to do that, we can use the right-hand rule, right? The second right-hand rule. Thumb is in the direction of the induced magnetic field. We can see that in order to have an upward induced magnetic field, the current has to be counterclockwise in this case, right? So current induced has to be counterclockwise. And we can see that EMF equals negative change in flux over time. Well, now this guy here is negative because you're decreasing the flux. Well, negative, negative, right? Negative, negative going to cancel, and you're going to have a positive EMF. And positive EMF means that it's going to be counterclockwise EMF, which is counterclockwise current, which again agrees with that. All right. So this is how we can use Lenz's law to understand the direction, or let's say get the direction of the current by just simply looking at the external magnetic field and how it's changing, and we can figure out in which direction will be induced current and induced EMF in our circuit. All right. So let me kind of do this. Okay. So then the induced current in a loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. That is, the induced current tends to keep the original magnetic flux through the loop from changing. All right, so hopefully it makes it makes more sense right now. All right, so then for example, let's look at over here. We talked about that if the conductor, if this moving conductor is pushed to the right, there is going to be a counterclockwise current. Okay, now we can try to even understand why. Okay, so consider the bar moving to the right on two parallel rails in a uniform magnetic field. Okay, so why is the current counterclockwise? All right, so we'll think of it like this. So what I have here is, this is my flux, right? All right, so let's say this is my flux, which, remember, it goes B times L times X, right? So let's say this is what we get, okay? That means magnetic field strength in this case is pretty much, doesn't change, right? Or, at least, in terms of, like, let's say what we get here is the flux is increasing as, let's say, you move this here, so your X is increasing, so your flux is basically as a function of time increasing. That means this quantity dB dt, right, is, sorry, not just B, but changing flux over time, right, is positive. Okay, because it is, it is increasing. Okay, then what do we get here? So think like this. So if it is basically increasing, and you have a magnetic field, right, that external magnetic field is into the page. So remember, the Lenz's law tells you that the circuit is going to try to fight that. Right? It's going to try to fight that change. Okay. How can it fight this change? Well, it can try to fight this change by inducing its own magnetic field. Okay. So it cannot change its own shape and things like that. But remember, so one of the things loop can do here is to induce current, which basically generates magnetic field. Okay. So in which direction should be the magnetic field? Well, magnetic field induced should be in the opposite direction of the external magnetic field, because it's going to try to change, right? Try to decrease magnetic flux. In order for it to try to decrease magnetic flux, it has to have an induced magnetic field in the opposite direction. That means induced magnetic field should be out of the page. All right, so if it's out of the page, that means your thumb isn't out of the page. It shows that the current has to then go counterclockwise. So that's why current has to go counterclockwise, because it has to generate out of the page magnetic field. All right, so as the bar moves to the right, the magnetic flux through the circuit increases with time because the area of the loop increases. Okay, and as it increases, right, so the Lenz's law says that induced current must be in such direction that magnetic field it produces opposes the change in the magnetic flux of the external magnetic field. So the flux into the screen and is increasing. The induced current, if it is to oppose the change, must produce a magnetic field through the circuit out of the page. And in order for us to get that, we need to have induced current that is counterclockwise, right? So if it is, when the bar is moving to the right, it's going to produce magnetic field out of the page, okay? And it's going to try to, fight that change, okay? So what happens if, let's say, the conductor is moving to the left? Well, if it's moving to the left, the flux is decreasing, and the flux is decreasing, is going to then try to reinforce the flux, increase the flux by pumping magnetic field into the page, right? This is the induced magnetic field into the page, and that means that the current has to be clockwise, as you can see, right? Because the magnetic field is into the screen, we're talking about induced magnetic field, right? It has to be clockwise to produce magnetic field into the screen inside the loop. All right, so that's why Lenz's law kind of like very easily, allows us to find the direction of the current. Okay, and that's why we can see that when the magnet was moving toward the loop or away from the loop, we would get two different direction current. Because when the magnet, let's say here, as you can see, right, in picture A, the north of the magnet moving toward the loop. And that means the magnetic strength is increasing. And the loop gonna try to change that by pumping magnetic field of its own in the opposite direction of the external. That means it's gonna try to have magnetic field to the left, right? To the left. And that has to be counterclockwise current, okay? There has to be a counterclockwise current, okay? Because this is that magnetic field generated by the loop. It has to fight against the external magnetic field, right? But here, if the magnet, the north of the magnet is moving away, that means here the magnetic field is decreasing. So it's gonna need to pump magnetic field in the same direction, right? So this is the B induced, right? In the same direction as the external magnetic field to reinforce it. And in order to have a magnetic field to the right, it has to have a clockwise current, right? So those are basically the ways we can determine, and this is the reason that ammeter was giving us positive or negative depending if it was moving toward or away from our loop. All right, so let's look at a couple of examples here. So you have a circular loop of wire is in a region of spatially uniform magnetic field as shown. So the magnetic field is directed into the plane of the figure. We want to determine the direction, clockwise or counterclockwise, of the induced current in the loop when B is increasing, the external magnetic field is increasing, or when B is decreasing, or when if you have the B as, let's say, constant. All right, so let's do this. So again, we don't have to calculate anything for this, just all conceptual. Think like this: into the page magnetic field, and it's increasing. That means the loop for part A has increasing flux, right? So has a, change in flux that is increasing. Okay, that is positive. Okay, it's increasing flux. All right, so what it's gonna try to do here is, well, technically since it's negative, right? So, so it's negative and becoming more negative. So technically, right, because magnetic field is into the page, so it's negative. So the flux is, I guess, the change in flux, right? So it's negative and becoming more negative. You can think like that. So, but you can think like flux is increasing. Well, as the flux is increasing, this loop gonna try to fight that. And it's gonna now try to have a magnetic field of its own. Again, when the flux is increasing, it's gonna try to have a magnetic field induced in the opposite direction. That means magnetic field induced B, right? So let's say induced should be in the opposite direction of the external magnetic field. That means it has to be upward, right? So it has to be upward or out of the page magnetic field. If that's the case, that means for part A, current has to be counterclockwise. It has to be have a counterclockwise current, because if your thumb is out of the page, your fingers curl counterclockwise. That means the current should be counterclockwise if the magnetic field is increasing. All right. So let's see what happens for part B. So for part B, magnetic flux, it says B is decreasing. That means magnetic flux here is decreasing, you can say, right? Well, if it's decreasing, that means the loop gonna try to reinforce it. That means it's gonna try to pump magnetic field same direction as original magnetic field. That means the magnetic field, you can see, right? Here the B was out of the page, and then here the B induced, right, should be into the page. And if that's the case, the current has to be clockwise. Okay, that means there has to be a clockwise current for us to get into the page magnetic field. All right, so then for part C, it says, what if the magnetic field is constant, doesn't change? Well, that means change in flux over time here is 0, which means EMF 0, which means current here is 0. That means no induced current or EMF. All right. Another example, you have two closed loops, A and C, are close to a long wire carrying a current I. That means what we have, one straight current carrying wire. That means there's a current running through that straight wire. And then we have two loops above the wire and below the wire. And they're not connecting to anything. So, but what we have here is, we know that if there is a current running through the wire, then there is a magnetic field generated by that wire. And using the right-hand rule, where your finger is in the direction, your thumb is in the direction of the current, we can see that everywhere above the wire, including through the loop C, this external magnetic field, right, is out of the page. And everywhere below the wire, the external magnetic field here will be into the page. That means through this loop A, there is an external magnetic field into the page. All right. Now, what we get from here is this. If the current is constant and steady, there will be, no induced current in any of those loops. But part A tells you that find the direction, clockwise or counterclockwise, of the current induced in each loop if the current is steadily decreasing. All right. That means the current in the straight wire is decreasing, which means the magnetic field is decreasing. That means the flux through both of those loops will be decreasing. All right, so let's look at loop C. Okay. See, for the loop C, magnetic field is out of the page and it's decreasing. That means the loop gonna try to reinforce the original magnetic field. That means the induced magnetic field that is generated by loop C should be in the same direction, right? In the same direction as the original one, because it has to reinforce it because it's decreasing. Well, what do we get? What type of current will give us that? Well, it will have to be a counterclockwise current, right? So the current has to be counterclockwise. How about for A? Well, for A, what we get here is this. So the magnetic field is into the page and it's decreasing. Again, loop A gonna try to fight it by pumping more magnetic field in the same direction because it is decreasing. That means induced magnetic field is also into the page. And what we get here is that is given by clockwise current. So then the current here is clockwise for the loop A. All right. That means in this region there's a clockwise current. All right, so part B says this. While the current is decreasing in the straight wire, what is the direction of the force that the wire exerts on each loop? All right. Well, because one of the things we have here is, if let's say if I consider this region of that loop C, see there is a current there, there's an external magnetic field due to the straight wire. That means it's going to be a force acting on this loop C due to that straight wire. And if you look at this particular region, right, that I chose, see the current over there is in the same direction as the current in the wire. And we learned, right? So if you have two wires with the same current, the force between them is going to be attractive. That means, you know, loop C is going to be pulled toward the wire. Well, there's also the top part of that, which has an opposite direction. So that part is going to be repelled, but this is further, much further than the bottom part. So overall, there's going to be pull toward the wire. Same thing with the loop C. See if I kind of like use this region here for the loop C, that region has a current in the same direction as a wire. And this wire then going to be, you know, pulling the loop A as well, right? This is loop A, sorry. And the other region of that has a current in opposite direction, let's say this part, right? But again, this is further, right? Compared to this, let's say this, you know, part one of the loop A. So overall it's going to be, you know, again, pull toward the, you know, wire. That means both of those loops going to be then attracted to the wire. All right, so let's look at this last example in this concept. So we have a circular loop of wire with a radius R of 0.0250 meters. Okay, so that's our radius, and a resistance of 0.39, you know, ohms. That's ohms over there. Is in the region of spatially uniform magnetic field. That means magnetic field is uniform in that region. So the magnetic field is directed into the plane of the figure. So it's into the page. At t equals 0, magnetic field is 0. That means, for example, right, if I'm finding the flux at t equals 0, it's 0 because there is no magnetic field. The magnetic field then begins increasing. It increases that by, you know, b of as a function of t equals 0.380. Some, you know, we can think like this is just a coefficient in front of it, right? Then t cube. Okay, so there's a unit of t per Tesla per, you know, cubic seconds, right? But let's say I can just ignore it for a little bit right now. That means that's the magnetic field as a function of time. It changes. That's why you can say, right, plug in t equals 0, it's 0. Plug in t equals 1, magnetic field strength is 0.38. T equals 2, right? Then that times basically, you know, 8 and so on and so forth. But, you know, as a function of time, it changes basically. Now, the question here is this: what is the current in the loop at the instant when the magnetic field is 1.33 Tesla? All right, so that's good, right? Let's say I can find, you know, in terms of what is the current at that instant. But, you know, one of the things I have here is, you know, there's in order for me to find the current, I need EMF and the resistance. And I don't know what is the EMF at that instant, because remember, my EMF here is, you know, has to be calculated from that particular, you know, change in flux. All right, so then one thing we can do here, we can say, all right, EMF is equals to, we can then again use absolute value here. All right, so then change in magnetic flux over time. All right. Okay, so then what we get here is, remember, so this is change in time, then this is BA and cosine theta, but we can see, right? So the magnetic field is perpendicular to the plane, so theta is 1 because of the vector A is also, you know, dA, you can say that it's also parallel, you know, to the magnetic field. It's also perpendicular to the plane, so the theta is 0 degrees. So it's just B times A. But here B is, you know, a changing, so this becomes basically A times dB dt, right? Or A times, you know, d dt of 0.38 t cube. Okay, so that's kind of what we get. All right, so then if I find this, right, then EMF here is equals to, well, area here is pi r square, and taking the derivative of that, I'm gonna get then 0.380, then 3 t squared. Okay, so that's what basically I'm I'm gonna get. All right. So then what I have here is, that's my EMF, right? So then I can, take this and divide by the resistor. So take that divided by the resistor of 0.0250 meters to find the current. So what we'll get here is this. So I'm going to get 5.73 times 10 to the negative 3 amps per second square, and this is then T square, right? So that means I can, those are all numbers. I can just basically calculate something from them, but let's say then I have the T square. So I get that. The thing is, let's say what I want to know here is I want to find when is the current when magnetic field is this value, but I need to know, let's say, when it happens, at what time, right, the magnetic field is that, because you can see, right, current here also depends on time. It's, some, 5.739 times 10 to the negative 3, which is coefficient, times T squared. So give me the specific time and I can tell you, what the current is. Okay. But one thing I know here is I know that, for example, let me kind of do it in this region. I know that magnetic field is equals to 0.38 T cube. So that means at the time, I can find the time where the magnetic field here, right, is 1.33, because it is changing at, 0.3, let's say same rate at any time, 0.38 T cube. So then I can say 1.33 is equals to 0.38 T cube, and just use that to find, the T. So basically divide those and then take the cube root. So I'm gonna get 1.518 seconds. That means when time equals 1.518 seconds, my magnetic field is 1.33. That means now I can come back to the current and I can say it's 5.739 times 10 to the negative 3, then times 1.518 seconds square. And that's going to be 0.0132 amps. And that's going to be basically my time when the current will be, or what's the current at the same time where the magnetic field is 1.33 Tesla. All right, guys, so